All right, so I wanted to do two example problems. This first video, what I wanted to do is an example problem of how we can use the force of gravity between two masses to find the total force on one mass that has two other masses acting on it. So this is going to incorporate the idea of the force of gravity, how big it is, and how we calculate it using the Universal Law of Gravitation. But it's also going to use our vector knowledge. So we're going to have to brush up on our vector skills. So the question is, I have three masses on the corners, three corners of a rectangle. I made the rectangle 3, 4, 5 arrangement so that the diagonal was going to be 0.5 meters. We're given the different masses, and the question is, what is the total force on mass 1 due to mass 2 and mass 3? So what we're using is the Universal Law of Gravitation, where the force of gravity is equal to the universal gravitation constant times the product of the two masses divided by the radius or the distance between the two. But the first thing that we're going to do is we're going to look at the picture and we're going to draw the direction of the force, because this is an attractive force. Masses attract each other. And so we're going to draw the force acting on mass 1 from each of the masses, mass 1 and mass 2 and mass 3. And then we're going to see how big they are using this expression. Then we're going to add our vectors. So when I first look at the force on 1 due to mass 2, of course it's going to be along the line that joins them. And because it's an attractive force, I'm going to call it F2. The force that mass 2 exerts on mass 1 is going to be in this direction because it's attracting it. I also am going to draw F3. That's the force that mass 3 exerts on mass 1, again attracting it, but it's going to be in the downward direction. Now I want to just figure out how big the forces are. So F2, I would be big G, mass 2, mass 1, the distance between them squared. So this is 6.67 times 10 to the minus 11. Mass 2 is 2 kilograms, mass 1 is 3 kilograms, and the distance is 0.5 squared. The magnitude of this force is going to be 1.6 times 10 to the minus 9 newtons. Remember, this is a really weak force, and I use small masses, and that's why all these forces are going to be very small. The magnitude of force 3 is going to be big G, mass 3, mass 1, the distance between 1 and 3 squared, and now we put in our numbers. And we find that this is going to be bigger because the masses are bigger, the distances are smaller. So that's 6.67 times 10 to the minus 9 newtons. Then what we have to do is we know we have a picture of what direction the forces are acting in. We have their magnitudes. Now I have to add vectors. We're going to add x's together, so the total x component is going to be given by the x component of 2 plus the x component of 3. Now 2, let's look at this angle. We're going to use that angle that I just drew there. If you do some calculations, I'll let you do it. You can use your trig know-how and figure out that that angle is 36.9 degrees. So the x component of force 2, it is in the negative direction. It's going to be 1.6 times 10 to the minus 9. That's the magnitude of F2, but then we're going to multiply by the cosine of 36.9. F3 doesn't have an x component because it's pointing straight down. So our x component of total x component is going to be minus 1.28 times 10 to the minus 9 newtons. Now we're going to find the total y component. That's going to be the y component of 2 and the y component of 3. In the y component for F2, we'll use the sine of theta, and it's also down. And that's why I put that negative sign there. And F3 is totally down, so I just add 6.67 times 10 to the minus 9. I shouldn't have said add, I should have actually said subtract. I think I was thinking add a negative. I know what I'm doing, don't worry. So the total y component is minus 7.63 times 10 to the minus 9 newtons. All right, so again, when we're at this stage, all of this should seem like review because we're simply adding vectors. The only thing that's really new here is we're using a new force, the force of gravity that exists between two masses. And we use that to draw the direction of the forces. Again, remembering it was an attractive force and we were interested in the force acting on mass 1. We know that the total magnitude will be found using the Pythagorean theorem. And when I do that, I find it's 7.74 times 10 to the minus 9 newtons. If I want to find the direction, I'm going to call it phi so that I don't confuse it with that angle theta. It's going to be the inverse tangent of the y component over the x component. And when I do that, I get 80.5 degrees. Now, I actually had a negative x and a negative y. And so I know that my F is in the third quadrant. So what I need to do with this angle is I need to add 180 degrees. And so I could say that it was 260.5 degrees from the positive x-axis. If I use the 80.5 degrees, I have to say down from the negative x-axis. Remember that when you find that angle, when you're adding vectors, you're not done until you really determine or explain how you're going to use that angle. So this is just an example. Again, the only thing that's really new to us is the fact that we're using the force of gravity. The adding vectors is the same. And I just want to point out that I made a mistake today and I wore a dark shirt. And so I look like a floating head. So I hope that you're not creeped out by this video.